Hi, and welcome back to Caroline's Chemistry. Today we're looking at the ideal gas equation and all of those pesky unit conversions. In this lesson, we'll understand what makes a gas ideal in the first place, break down what each term actually means, and how to handle the units, because they're the number one reason A-level students lose marks here. Finally, we'll apply the equation in some real questions. By the end, you'll see how this isn't just a random equation to memorize. It's one of the most elegant shortcuts in all of chemistry. Let's dive in. Now, I'm always keen on you being able to fully understand why we're doing what we're doing, rather than just trying to rote learn something. So, quick note on what do we mean by an ideal gas anyway? And what we are doing when we say an ideal gas equation is we're making a set of assumptions. In order to be able to do these calculations, we assume that they are ideal gases, i.e. there's no forces between the particles and the sizes of the particles is negligible. It's a good approximation because obviously there are forces between particles, say van der Waals forces between the atoms. But by assuming that there aren't, it gives us this good approximation to work with. This is the ideal gas equation that we're going to be working with. PV equals nRT. P stands for pressure. Now, there are a lot of standard units here, and when examiners are making up questions, it's a great way to hit higher level maths marks to start to build in all of these different unit conversions. So expect to do that. Expect to have to convert a lot of units. So pressure is in pascals. Everything, no matter what you get, whether it's kilopascals or megapascals, has to be converted into pascals. Volume is in meters squared. Now, this is pretty much the only place that we work with meters cubed even, that we work with meters cubed in chemistry because it's a very big measurement. Like usually we're working with centimeters cubed because that's the amount that we can handily use in a lab. So centimeters cubed are the smallest. 1,000 centimeters cubed fit into a decimeter cubed, and then 1,000 decimeter cubed fits into a meter cubed. N is the number of moles. R is the ideal gas constant, 8.31, and T is the temperature in Kelvin. So a quick reminder about how to convert these units. So for volume, remember centimeters cubed, that is the smallest measurement, and 1,000 centimeters cubed fits into 1 decimeter cubed. So you have to divide by 1,000 to turn centimeters cubed into decimeters cubed, and here as well. Decimeters cubed into meters cubed, there's 1,000 decimeters cubed in a meter cubed, divide by 1,000. We do the reverse if we're going from meters cubed into centimeters cubed. And it means if you're going straight from centimeters cubed to meters cubed or vice versa, then the factor is 1,000,000. Same idea here for pressure. So pascals is the smallest. So in order to convert into kilopascals, then we divide by 1,000. To go from kilopascals to megapascals, we divide by 1,000. Factor of 1,000,000 overall if you're going from pascals to megapascals. And vice versa if you're going from megapascals into pascals. Temperature is nice and straightforward here. So K stands for Kelvin. Remember, you take the degrees Celsius and you add 273. So when we do ideal gas equations, we're always going to start with writing down the equation. So PV is equal to nRT. The question is asking us to find out how many moles. So now let's write the rearranged equation. So N, we're going to divide everything by RT, and that therefore equals moles equals PV over RT. So always show the rearranged equation so that you can get marks for it if you go wrong later on. Now let's consider all of the unit conversions that we need to do. So pressure, P. We're given 101 kilopascals, so we have to times by 1,000 to make it into pascals. V, so for the volume we're given it in centimeters cubed. So centimeters cubed into decimeters cubed is divided by 1,000. Decimeters cubed into meters cubed is divided by 1,000 again. So I'm therefore going to divide by 1,000,000, giving me 0.0194 meters cubed. Does So that's the 19,400 centimetres cubed divided by a million. Then R, 8.31, the gas constant, ideal gas constant, and temperature, we'll take the 27 degrees Celsius, add 273, and that gives us 300 Kelvin. Now we're ready to substitute into our rearranged equation. So N is equal to 101,000 times by the 0.0194. I advocate using brackets on your calculator, otherwise you might end up with a calculator error. And then divide that by 8.31 times by 300. And if we tap that in, we get 0.786 moles. And then we're just going to check our number of significant figures. So each one of those numbers given in the question is to 3 sig figs, so our answer should be as well. So for this question, we're asked to calculate the temperature. Let's start the same way by writing out the equation. PV is equal to nRT. In order to find out the temperature, we're going to divide both sides by nR. So that becomes PV over nR. Now let's consider each of these terms and any unit conversions we need to make. So starting with the pressure, we're given 90.0 kilopascals. Now we want this in pascals, our standard units, so we're going to times that by 1,000. So therefore we have 90,000 pascals. Then let's look at volume. So volume is given as 2 decimeters cubed and we want it in meters cubed. So I'm going to have to divide by 1,000 there because 1,000 decimeters cubed fits into 1 meters cubed. Then we have our N that we're given as 0.140 and R, our ideal gas constant, 8.31. Let's now put our numbers into a rearranged equation. So we have 90,000 pascals times by the 2.10 to the minus 3. And again, I advocate using brackets here in your calculator so you don't make a calculator error. And then we'll do that divided by the 0.140 moles times by the 8.31. So put that into your calculator line by line, and we overall get 154.72. Not quite our final answer. We need to consider the number of significant figures, and every single one of those pieces of data that we originally started with and use is 3 sig figs. So therefore our final answer to that 3 significant figures is 155 Kelvin. For this final example, the most complicated one, we've got a bit more to do. So we're asked to calculate what volume of hydrogen gas is produced when 1 gram of sodium is reacted with excess water. Now, can you see the difference here? We've given data on the sodium, but we're asked to find out about the hydrogen. So we essentially have to work from the sodium, work through to the moles, in order to work out the moles of hydrogen gas, to then be able to work out the volume. So this is going to look very similar to a reacting mass calculation to begin with. And if you're thinking I'm a bit rusty on that, then head back to the video that I made on reacting mass calculations, and I'll talk you through this method from scratch. So we have a mass of sodium, 1 gram, and we're asked about the hydrogen. That's our question mark. To construct our table, we'll pop down the sides here. Mass is over Mr. Moles. Putting in now the 1 gram of the sodium and dividing by the MR, or the AR in this case because it's an element. And in order to work out the moles, we do 1 divided by the other, and that equals 0.04347 That's our moles of sodium. Now to convert and switch columns to the moles of hydrogen, we take into account the reacting ratio, which is 2 to 1. So I'm therefore going to divide by 2. So that gives us, once we put it into our calculator, 0.021739. That's our N for hydrogen, our number of moles. Now we can work with the ideal gas equation. So we're asked to work out the volume. let's pop in the equation to begin with and then rearrange for volume, dividing by P. So that's nRT divided by P. Now, the terms for this equation, we have R, 8.31. We have N, 0.021739. We just calculated it. We have the temperature that is handily already in Kelvin, 298 Kelvin. And the pressure that we do need to convert because we're giving kilopascals and we want pascals. So there we times by 1,000 to turn it into pascals. Now let's substitute these values into our rearranged equation. So we have our N, 0.021739, times by R, 8.31, times by T, our 298. Make sure you pop that in brackets when you're putting it into your calculator and divide it by the pressure, 100,000. Our volume therefore comes out as 5.38 times 10 to the minus 4. And remember the standard units here is meters cubed for volume. Double checking the number of significant figures that our answer is 2. All of the data in the question that we used was 3 sig figs, and that is 3 sig figs for our answer.
Thanks for watching, and if this was helpful, then don't forget to hit like and subscribe now for new chemistry videos every single week so that I can help you do your best in your GCSE or A-level chemistry.